and also talk about my research, which is privacy-preserving machine learning. Yeah. So let's start. Is there anybody who doesn't have email address? I don't have email address. I just don't like online life. Nobody, right? So the point I wanted to make in this first slide is that increasingly more and more devices collect and stream your data. And we all have email addresses, right? We at least check our email maybe once a day. And if you're rich enough, you can afford also smart home appliances, right? Your fridges collect all the data. I mean, it's called Silicon Valley. They have this fridge that collects all the data, right? You're laughing, so probably you know. And drones, they also collect data and stream it somewhere to somewhere. But what worries us is that in many cases, our data is owned by only a few corporations. I don't need to name this because this is recorded. But you know which companies we are talking about, right? So, and also we don't know whether they will abuse our data, and this is concerning. I will give you an example that's actually really scary. So this doll is called Kayla. So this Al Jazeera News says this is a spy doll, and the children's toy raises privacy issue. Why? Because Kayla is a smart toy. It can interact with children. One of the members of Norwegian Consumer Council, his name is Finn Maistad, I don't know how to pronounce his name. Finn, he actually had a TED talk on this product called Kayla, and he pointed out two things. One is the conversations you do with this machine or doll can be streamed to companies' server, and then they can actually make money out of the data. And anybody who has a Bluetooth connection to this machine doll can actually hack this doll. So this is an example in his TED talk, shows that he's actually connecting to this doll. You see this microphone, right? So whatever he says, this machine is actually saying it. So you can ask, hey, where is your mom? Is your mom coming home soon? You can ask these kind of questions. So it can be very, very scary. Of course, in Germany, where I work and live, this doll is not available. And I heard they are actually in this, what is it called? I don't know, spy museum or something. It's actually confined there, so you cannot get this doll, but still there are some countries that can have this kind of doll. And probably a lot of products we use without even knowing they are streaming our data, right? So this kind of threat make us think about privacy issue. And another thing is actually, this is more interesting to me. Why I think about privacy is for this philanthropic reason. So in this example, this speaker talks about the importance of sharing data for public good. And I think she works at a FedEx, or I don't know. You can just Google her name and then watch her TED talk. So in her talk, she basically says, your company's data could help end world hunger. And she talks about it. But then the idea of actually sharing data for public good is actually not from her. It's from United Nations Global Purse. It's called data philanthropy. So a lot of data owners, these are private sectors, share data with public sectors for public good. So why they thought about this thing is because now they think about big data as a new kind of natural resource. Yeah. It's infinitely renewable and increasingly ubiquitous, but unfortunately, at the moment, this is fallen into the hands of industry. But it's our responsibility, social responsibility, to realize that data should reach the people who need the most. But then, I mean, even if we want to share our data, we don't want to lose our right, which is privacy, right? So we have to also think about privacy in that sense. Yeah. So this is a motivation why we will probably need to think about privacy. I mean, the first thing is, well, just anonymize data. I mean, why do you need this very, very complicated technology to protect your privacy anyway, right? But I can give you the example that just anonymizing data, anonymizing, what I mean by anonymizing is just removing the obviously identifiable information is not enough. I took this example from Sweeney 2002. I think at the time that person was a graduate student. The person actually showed that by combining several, maybe in this example, 2 publicly available data sets, you can identify an individual, even if the data sets were released after anonymization. So in this example, the first data set was published by Group Insurance Commission that has lots of individuals' information on what kind of medication they took, how many total charge they had, what kind of procedures they got, their gender and zip code. They removed the exact address and the date of birth and so on. Yeah, but this is the data set that had. And there was another data set. It's Cambridge voter list. Obviously, this is a voter list, so this is publicly available. And it has a name because it has to show the candidate's name, right? And party affiliation and address, zip code, sex, and so on. Yeah. And unfortunately, there were 6 people listed, and among them, 3 were men, and only 1 person lived in that particular zip code area. So the author of this paper was able to identify that person, who was a governor, William Weld, in that Massachusetts state. And now the information on this person's illness, what kind of illness he has, how much money he paid, and so on, is all public. Now we know this information that he probably doesn't necessarily want to share with everybody in the world. So simply anonymizing data is not enough. What about releasing statistics? Suppose I have this privacy-sensitive data. It's hidden here behind privacy wall. I will just call it privacy wall. So nobody can access it, but I can just release maybe some statistic from the data. I will just call this X transpose X and X transpose Y as the first and second moments. I will just release this thing to public, right? I mean, individuals' information is hidden in the statistics, so I wouldn't worry that, it's gonna be a problem. But, of course, there are more advanced attacking methods. I will give you an example. Suppose there is an adversary that has a prior knowledge on a certain individual, YN and XN. So these are input-output pairs for this individual who happen to be in this data set. And this adversary knows some of the input attributes, but some of the input attributes that he doesn't know, but he wants to identify it. And he basically uses this publicly available statistics and compute the least squares solution, yeah? And then he can wiggle the things that he doesn't know, right, in this input attribute to match these 2 values. and he can probably obtain statistically sound prediction of sensitive attributes. Something like that. So just simply releasing statistic is not enough. So we need some more provably strong notion of privacy. Okay, so I will mainly talk about differential privacy today. How many of you here ever heard of differential privacy? Oh, okay. 8 people. Thank you. Okay. So in plain English, don't worry, I will go through this thing very slowly because it's like one of the important things that you have to understand from this lecture. Differential privacy is, this person is not a scientist, I don't think so. He's a journalist, he's writing it in a plain English, so I will read what he says about differential privacy. Differential privacy is the statistical science of trying to learn as much as possible about a group, right? You want to extract the information from a group while learning as little as possible about any individual in it. So it looks like it's a little bit conflicting, but it is possible. I will illustrate this a little bit more. So suppose there's a data set D1 I denote. Yeah? This D1 data set has a lot of people's data. Maybe we can call this as in medical data. So each individual's weight, height, and a lot of biomarkers and so on, they're all here in this data set 1. And this data set includes these people's information as well as Alice's information. And we run some randomized algorithm A, given data set D1. And this is some output we get from this algorithm. Okay. Now let's consider another data set, D2. D2 has exact same people's information, the same information as D1. But now we will replace Alice's information with Bob's information. Okay. And then we will run the same randomized algorithm A. And what we hope to get is somewhat similar output as before. So from an adversary's point of view, who can only see the outputs, right? The adversary cannot know whether Alice was in the data set or Bob was in the data set, even if he knows all of these people's information, if these outputs are very similar. So this is what differential privacy tries to do. Okay? This D1 and D2, we call it neighboring data sets. So why? Because n-1, let's say n is the number of people in the data set. n-1 people's information is the same in these 2 data sets, but only one person's information is different. And in this case, we call these data sets neighboring. Okay. Now, more mathematically, we call an algorithm, this algorithm we just saw, A, is epsilon differentially private if this thing holds. What is this? So this thing, this L of O, is called privacy loss. Yeah? Privacy loss is nothing but the log probability ratio. So the first probability is the probability of the algorithm given D1 outputting certain output O. And second probability is the probability of the algorithm given dataset 2, D2, output the same, exact same O, if this quantity is bounded by epsilon, and this bound should hold for all possible output O of the algorithm A, and also all pairs of neighboring data sets. So this sounds very stringent, right? It has to hold for all possible outputs and all possible data sets. So epsilon. Epsilon basically quantitatively measures how much of the risk to an individual privacy may increase due to that the individual's data inclusion in the inputs to the algorithm. So maybe this is a little bit not clearly explained. But so intuitively, large epsilon means you have a lot of difference between these two, right? So the adversary can know the difference easier than the case where epsilon is small, right? So then large epsilon is more private or small epsilon is more private? Which one is more private? That's right. Then you got it. Okay. So now I can move to the next slide. Okay. So then we just learned about the definition of epsilon differential private. So an algorithm is epsilon dp if the privacy loss is bounded by epsilon. And how we actually apply this to machine learning techniques. Yeah. So I will talk about this thing a little bit. Let's say there is a sensitive data as an input, and we want to compute something, some function, given the data. Let's say the easiest thing is average of average income of the people in the data set, something like that. And the easiest way to release the output as dp is by adding noise, such that the resulting quantity has the limited privacy loss, right? The bounded privacy loss. And I will talk about the examples of Laplace noise and Gaussian noise. These are all corresponding to Laplace mechanism and Gaussian mechanism, respectively. I will talk about this thing. But what's important is, whatever noise you add, the noise variance should follow this. Then we can say the resulting quantity is epsilon dp. So why do we need to have this kind of constraint is to make this privacy loss bounded by epsilon. It's actually reverse engineering. You think about the definition and then what is the noise variance, right noise variance for making the output epsilon dp, right? So something like that. So I will talk about these two quantities, what these are. So this epsilon is privacy loss. We saw it before, right? And then the numerator is called sensitivity. Sensitivity is defined by the following. So it's a maximum difference in your function that you calculate. And you find maximum over all pairs of data sets, the neighboring data sets. I denoted by D1 and D2, but in this case, I somehow flipped the sign. So it's like not sign the notation, D and D prime. These are neighboring data sets. So this is a notation people use. The distance between these two is not any fancy distance, it's just a Hamming distance. So one entry difference between these two, and we want to find the maximum of the function. If you think about it, if you allow for large privacy loss, right? Large means you can have very small noise variance, so you don't add so much noise. So if you don't add so much noise, then it's gonna be, the final value will be closer to the true value without noise. So it's less private. And then if you, the quantity you compute happen to have a very, very high sensitivity, that means one person's change actually can incur a lot of change here, right? To hide that effect, you have to add more noise. Okay, some people are nodding, thank you. Back there, can you understand? So I will quiz you, I will just repeat what I just said. If your function that you compute has high sensitivity, do you have to add more noise or less noise to hide this? More, yes, thank you. You got it, you got it. Okay, so as you saw, there is an inevitable privacy accuracy trade-off, right? So as I said, noise is proportional to, noise variance is proportional to sensitivity squared and then divided by privacy loss squared. And in user case, the non-private methods, usually, there's no privacy loss change anyway. So the accuracy will be some constant. But differential privacy methods has this function as a, this becomes a function of privacy loss. So if you allow for large privacy loss, your accuracy will go up, but your privacy loss will be larger, right? So there's a trade-off. But what we hope to get is, in the end, good differentially private machine learning algorithms. Well, what I mean by good is it produces good accuracy, relatively good accuracy, with the relatively acceptable privacy loss. Okay, so there is this trade-off that you have to play with. Yeah. Okay, good. So now I will give you some example mechanisms. So I talked about Laplace mechanism, Laplace noise and Gaussian noise. So I will talk about these mechanisms using this noise. First, Laplace mechanism. Suppose my input is some part of data set, monthly salary, and this is individual one's salary, individual two's salary, and so on. And we assume that this is bounded by, nobody makes negative income, right? So bounded by 0, and some, I don't know, 300, I just chose some number. Okay, so it's bounded. If it's not bounded, we can also scale down such that it is bounded. And then the intended output is the average monthly salary of these people in this group, yeah? And then this is the formula for average. And suppose, I mean, before we even go to this thing, right? I will just repeat why this is important again. Crick knows all of ours input, income, monthly income. He doesn't know my income. He wants to know my income. And this algorithm outputs the average income of this group, right? And if he knows everybody's income, this will reveal my income too. I don't want that. I don't want him to know my income. It's highly private. So what I'm going to do is I will actually ask the algorithm, hey, you add noise, okay? So that the average income is differentially private. And as we saw before, whatever noise we add, but in this particular case, we talk about Laplace noise. And the Laplace noise has the parameter here, right? The variance, no, it's actually, the variance of Laplace noise is actually 2 times of square of this thing. But the standard deviation is roughly proportional to the sensitivity of the average salary and divided by the epsilon. Okay. I mean, in this case, the sensitivity is actually quite trivial to compute, right? Anybody knows what the sensitivity is in this case? So I will repeat this, what it is. Can you see this? I wish I could pull this a little bit up. So the maximum difference between these two average salaries, if there is 1 data point difference in the data set. Okay, what is the answer? Oh, maybe I will talk about this. Why do I care about having limited input bound here? So average, right? Average is written this way. If there is 1 data point difference between these two, oh, can I use this thing? Oh, fancy. Okay. But maybe this is too obvious. Maybe I don't need to even write. Anybody knows the answer maximum? Huh? Divide by n. Yeah, right? Yeah, this is very easy actually. Can I write this? Okay. So the sensitivity of X thing, this. So this was the definition, right? And then I will now go to here. Max. N minus 1 xi plus x. Let's say the one data point difference incurs at the last data point. I mean, it doesn't matter, but let's just assume this way. Yeah, 1 minus n. Yeah, so now you can cancel these because they are exactly the same values, right? Okay. And then when is this largest? I think actually the worst thing is you can use the triangle inequality and do this 2 times and the largest thing, which is 300, right? This is the worst thing you can do. I mean, you can also see, there's something that I want to emphasize here. You can see that this n factor, if you have a very big data, yeah, n is very large, then this noise can be small, a lot smaller than the data set that has like very small size. So the sensitivity also changes. I mean, it also depends on what function you compute. In this average case, we can see that the sensitivity scales with 1 over n factor. Yeah. Okay, good. It's not so hard, right? Okay, so now I just told you how to use the Laplace mechanism to make the average input salary epsilon differentially private. And I will just simply prove it following the definition of privacy laws, whether this is actually DP or not, right? I don't know, mathematician, I think there are some people who are mathematicians that they want to prove things. So I will just satisfy their, yeah. Okay, so we will first look at the privacy laws, exponentiated. But the privacy laws is actually log probability ratio, but I will exponentiate it, and then I will look at this probability ratio. And because these are following Laplace distribution, it's probability 101, right? So you can see the PDF of a Laplace distribution looks like this. This is basically flipped, right? And we are evaluating at the same output O. So you can also use triangle inequality, cancel this out, and then you get this thing. And now you see the definition of sensitivity, which has this form, right? So you can bound this as epsilon. So your probability loss is bounded by epsilon. So this mechanism is dp. Now let's go to Gaussian mechanism. Gaussian mechanism is a little bit more complicated than that. So noise standard deviation. Previously, the noise standard deviation for Laplace mechanism was something like epsilon, sigma is proportional to, without this C thing, right? S and epsilon. But Gaussian mechanism, because Gaussian distribution has certain tail behavior, so we need this thing, this constant, which is a function of delta. So basically, we can state that if you add Gaussian noise to the function you compute, the probability that the privacy loss is larger than epsilon is bounded by delta. What it means is that the resulting quantity, yeah, this whole thing is epsilon dp with probability 1 minus delta, L is 1 minus delta. So the proof is very very lengthy, so I didn't put it here. If you are interested, you can look at this book, Algorithmic Foundations of Differential Privacy, that Cynthia Dorg and Aaron Roth wrote in 2014. Appendix 1 or A has this proof, so you can look at it. I just went over 2 examples of DP mechanisms, Laplace and Gaussian. It looks quite simple to do, right? Now I will talk about properties of DP. Because of these properties, now we will have some challenge that we have to deal with. But the first one is actually pretty good. It doesn't, I don't know, yeah.
So is adding noise the only way that we can do to guarantee the differential privacy, or is there any other way that we can do as well?
So roughly speaking, there are probably, broadly 3 ways. One is adding noise that we saw before. Or you can think of sampling as a DP mechanism, because sampling induces uncertainty anyway, right? And then the third one is, I will talk about this example later, but it's also a type of sampling, but I will talk about this thing later, yeah. So the 2 properties of differential privacy, the first one is post-processing invariance. So this is what I mean by post-processing. Let's say there is a sensitive data as an input, and there's an epsilon DP algorithm, and the output of epsilon DP algorithm goes into another algorithm as an input, but there's no arrow from sensitive data to another algorithm. It only post-process the output of the epsilon DP algorithm. Then this output of this algorithm is still epsilon DP with respect to the sensitive data that the epsilon DP used, okay? So, this makes things very easy. Let's say now we computed the monthly salary, right, in a differentially private way by adding Laplace noise. Now I give it to you, and you can do other things with this quantity without worrying about privacy of the original data set. Okay. Another property is composition. So sensitive data is as an input, again, and then we are considering 2 different algorithms. One is epsilon 1 DP, the other one is epsilon 2 DP. Then the union of these 2 outputs is epsilon 1 plus epsilon 2 DP. So, what it means to us for machine learning people is that the more we access to data, the worse the privacy loss will be, right? So, a lot of algorithms are iterative, meaning that we access the data over and over again. If you think about stochastic gradient descent, right? You keep accessing your data. Then this kind of composition will make things worse. So the total privacy loss will be very high, which you don't want to have in the end. So there are a lot of work on finding more refined composition methods than this linear composition. Linear, what I mean by linear is the adding up all the privacy loss. So which I will talk about as well. So these are 2 key properties of DP, post-processing invariance and the composition. Okay.
So the second point for the composition, it's like, can we say that it's like, if you do the sampling, the data, eventually at some point, you will get the whole set of data anyway, something like that? Not really.
In a way, yes. In a way, yes. But subsampling has also different privacy notion, but yeah, we will get to that point as well. Okay, so now I will talk about several examples of how one could apply differential privacy to machine learning algorithms that we know. I don't know if you guys learned about clustering and density estimation. I guess you did, right, during the first day? Density estimation, yeah. So I have 3 examples here. I will talk about density estimation, clustering through a mixture of Gaussians. And another one is topic modeling. And the third example is deep learning, to show how differential privacy can be applied to these examples. So the first example is clustering and density estimation. Let's think about mixture of Gaussians first. Who doesn't know mixture of Gaussians? This is something new. I never heard of it, and I'm scared. Okay, there are some people who are scared. Okay, don't worry. Okay, so mixture of Gaussians is basically a model you can use for clustering or estimating the density of your data, right? So these black dots indicate data point in some data space, okay? And mixture of Gaussians is basically assigning a Gaussian to learn each cluster, right? In this example, I assigned 2 clusters where the cluster center is written in terms of mu k. So k is the index for how many mixtures you will consider. And mu is the mean location. So this is mean location for this guy. This is mean location for the other guy. And we want to parameterize the Gaussian in terms of the mean and variance, right? So the variance basically tells us how large the cluster can be. And mean is where the central location is. So these are the parameters of this model called mixture of Gaussians. And we also introduced the latent variables, which I denote by L, I, and K. I is the data index. K is the cluster index, right? So that it can tell us the membership. My data point I belongs to cluster K, yeah, with what probability and so on. Okay. So the goal of so, I mean, you can parameterize this thing, but the goal is to identify what these parameters are to understand your data better. Okay, and to do that, we consider an algorithm called expectation maximization. I never heard of expectation maximization. Okay, I mean, this is a traditional method, and it's good to know, but I guess not many people use it. Yeah, but it's good to know. Yeah, good to know. So, okay, the model we talked about is mixture of Gaussians, and the algorithm we are using is mixture of expectation maximization. And under the model, we can make the following graphical model. So latent variables, Li, corresponding to each data point, Di. Yeah, the observed variables are shaded like this way. And then there are n different realization of these data points. And there is a model parameter, the mean location, yeah, and then the variance of each cluster affects your observation this way, okay? And what people do usually, you want to maximize your data given your parameters, right? Given your model parameters. But unfortunately, when you have these latent variables, this maximization, low probability of your data is not tractable usually because you have to integrate out the latent variables. So what people do is they use some tractable form of approximate distribution for the latent variables, and they lower bound the exact log likelihood. This has many names, but this lower bound, let's say we call this, let's say this is a free energy. I mean, I think if you're from physics is negative free energy, but so let's just call it free energy. And we want to maximize its quantity so that this lower bound can be as close as possible to the log likelihood, the actual log likelihood. And this has two steps. We have two steps to obtain the highest lower bound. The first step is E step. I mean, you can see this E step is from expectation. In this step, given the parameters, you want to maximize the free energy by tuning your distribution over the latent variables. Okay? And then, so this parameter T-1 means parameters you get from the previous time step. And then now you obtain your current estimate of the latent variables by maximizing this free energy. And in the M step, maximization step, you also use this, the current estimate of the latent variables, and try to maximize this thing by to obtain the parameters of at this time step t. Okay, so you do these two things to obtain the best parameters, model parameters that describes your data. How do you apply DP here? So that's the paper I work on. So I will just briefly mention how DP works here. But before that, so the EM algorithm has this form. I will repeat what EM does exactly. Sensitive data, you compute your estimate of the latent variables, right? And then you update your parameters. This is E step and M step. Yeah. And then given this guy, becomes an input to the update of the latent variables in the second step, as well as the data. And then you update your parameters, and so on. In the end, after J updates, you get these results. So here, the green arrows basically indicate how often I access the data. Okay. If you remember, the goal of expectation maximization, the goal of mixture of Gaussians is to estimate the parameters so that you can use it to see your data better, clustering or density estimation and so on. So, I mean, the things that you need to release is the parameters. So the idea is, well, then maybe let's just apply DP mechanisms to perturb the parameters, right? This is the most obvious thing to do. So this is basically what you can do. You perturb the parameters and output the perturbed ones. But I mean, something you need to make sure do correctly is the sensitivity analysis. You know, how much change you can get in the parameters if there's a one data point difference in the neighboring data sets. So here, because you have to compute the sensitivity, not only the difference in the data set here, right? Directly coming from the data set, that's what I mean, directly coming from data set. But also, the latent distribution also changes if there is a one data point difference. So when you do the sensitivity analysis for these parameters, you have to consider both cases, how much difference you get directly from the data, but indirectly through the latent distribution. So this is something I wanted to explain without showing equations. And then you do this in every step. Yeah, basically you get this thing in the end after J step. And you might wonder, oh, shit, but these guys are actually also containing information about data. Why are you not perturbing these guys? But first of all, perturbing these guys actually incur a lot of noise addition because latent variables are defined per data point, right? So there will be no 1/n factor like that. So larger data set doesn't necessarily reduce the amount of noise. So it's also what we actually need is the parameters to do more testing and so on. So we assume that these computations are all done behind the privacy wall. So we never release the latent distributions to minimize the amount of noise to add. Okay. Okay. Another thing you saw, maybe you might wonder, actually, this is something we need to discuss. You might wonder, why do you need to add noise to all of these steps? 1, 2, 3, and J, you know? Why don't you not just add noise to the last step? Because this is the one that you release and you will use anyway. The reason is, we don't know how to analyze sensitivity here. We don't know how one data point difference in the data set will result in how much difference we will make in the parameters. But here, this is doable in one step. Within one step, this is doable. But if there are like several steps like this, we don't know how to do it. I mean, that was the reason why we decided to do in this repetitive access and then do this analysis noise addition per iteration. But this actually introduces complication in terms of privacy loss composition, right? So there was a composition method that we have to think about how these all compose in the end. As we saw, the linear composition method was not so good. You can just add them up. The method itself is easy, but the amount of privacy loss you get in the end is very high. And Abadi et al., these people introduced a method called the moments accountant. It basically tells us how to find the smallest privacy loss after many, many iterations. And this is how they did it. First of all, they treat the privacy loss as a random variable. So, and then if you think about the Gaussian mechanism, for instance, if you add Gaussian noise, the privacy loss itself also follows the Gaussian distribution. And in that case, you can look at moment generating function of the Gaussian random variable, right? And then convert the moment bound to tail bound to get, I mean, this actually is done very easily by Markov inequality. And you can get a very strong privacy guarantee. If you're interested in the details, look at this paper. I will not go over this derivation, or you can also come talk to me later on. But what I want to emphasize here is that by using this moments accountant, this kind of converting moment bound to tail bound, this trick, you can get very, very small privacy loss after many, many iterations. This is a simple plot I made. So the total privacy loss after 100 iterations, assuming that per iteration loss is 0.1. So per iteration, you consume epsilon equals 0.1. And then after 100 iterations, under linear composition method, you get epsilon around 10, right? And there is a little bit more advanced composition method that still gives you, oh, there's no number here, but it's above 5. And the moments accountant method I just talked about briefly, this actually results in less than 1 total epsilon. So it actually provides really strong privacy guarantee for the same per iteration loss. So we use that and apply this to DP EM algorithm. I will show you an example where I use this. So we got this data from this web page that basically shows a abortion rate, where abortion happened in Germany. So this is a longitude, and then this is a latitude. Each dot indicates where the geographical location is, and these cluster basically is done by their marital status. So they are single, or they are widowed, or divorced, or married. So there was interesting cases. The one person married and got abortion, in such a year. I don't know exactly when the year is, but if you actually run this DPEM algorithm, what happened is even in this very small number of members in this cluster, you cannot identify the exact location of this individual because we add noise and move around. And then because we have only one data point, we will have a high uncertainty. Okay, so this is an example. So now I will talk about second example, topic modeling. I think, so I flipped through the natural language processing slides, but he only talked about the sequence to sequence, training and estimating what's the next word that will appear, something like that. But the topic modeling is just slightly different. He didn't talk about topic modeling, right? Yeah. So topic modeling is basically, given some number of documents, you want to organize them. Like how? By assuming some vocabulary set, yeah, and then you also assume some number of topics, and see how many words are in the vocabulary appears under this topic. So, for example, I took this slide from David Bly, who invented this latent Dirichlet allocation, which I will talk about later. So this is an example. You can see in this document there are a lot of words, and then he colored topics differently. Different color indicates different topics. And then you see under this topic, Jean has a probability 0.04. And it's hard to see. I guess this is a brain kind of topic. It has brain 0.04, neuron 0.02, nerve 0.01, and so on. So you can see somehow coherent words appearing under the same topic, right? So this is what I mean by organizing documents. So topic modeling, the goal is allocate words to topics and assign probability to terms in the vocabulary we assume in each topic. Okay. Latent Dirichlet allocation is the one that David Bly and his group proposed, and it has the following graphical model. This is kind of not so friendly, I guess, but I will just explain what these are, and then the important parts that we have to take from this graphical model. So the word, each word, W, and D is the documents, N is the word count, yeah, N, word index, sorry. And then we also, this guy has some hierarchy. This probability of the word appearing depends on several variables, random variables. The first one is probability over terms in vocabulary, it's denoted by beta, K. K is, indicates a topic, as well as the topic assignment of each word. So Z, D, N. This acts like the latent membership assignment in the mixture of Gaussians. And then there's another hierarchy that determines topic assignment of each word, denoted by topic proportion theta of each document. Okay. So, but there is a hierarchy. So these are both latent variables, and this is the parameters. Yeah. So now we have latent variables and parameters. Now you think, oh, maybe we can use EM to learn these parameters. But I guess you can use EM, but in this paper, they propose to use the stochastic variational inference. But I would first talk about variational inference. So as we saw before, in EM case, model parameters are deterministic. What I mean by deterministic is that there's no randomness in the model parameters. But in the variational inference case, we assume that these are random variables as well, and we will define the distribution over it, and we will learn that distribution. So now log marginal likelihood we saw before looks like this. previously, we only talked about the distribution over latent variables, but now we have variational posterior, the distribution over the model parameters. If I say posterior, you talked about Bayesian a little bit, right? Not really. Okay. For now, let's just think about posterior as a distribution over the parameters after seeing the data. Okay. So now we want to also maximize this quantity. Oh, sorry. Maximize this quantity, which we call variational lower bound, to get as close as possible to the marginal likelihood. Okay. And to do that, we also update the distribution over latent variables and parameters together. Okay, so this was the figure I used for EM, yeah, right? Latent variables and the model parameters. But if your model falls into this exponential family distribution, which can be written in this form. So this is the joint distribution between your data point and latent variable given the parameters. Can be written in terms of this. This is what we call natural parameters. And the other term is called the sufficient statistic. So what's important here is not the names, but the ability to distinguish these two terms. So one term is only a function of the data and latent variables, right? And the other term is the function of parameters. If you can do that, you can make this variational inference algorithm just like EM case, but with one exception, that now we noise up parameters. We change noise up parameter part to noise up sufficient statistics. So the detail of this thing is written in one of my papers. So you can use the same technique as DPEM. But if that's the only thing, then there will be no paper, right? So there are more complicated things than that. One thing is, unlike the DPEM paper, so we consider topic modeling. Well, usually topic modeling, we consider really large data set, like 1 billion data points and so on. So here, I mean, using the entire data at every training step, it's infeasible. So usually people use this stochastic learning, meaning that you subsample your data and then you evaluate your loss or variational lower bound, right, on those subsampled data. But in terms of privacy, there is an interesting effect, something called privacy amplification effect due to subsampling. So this theorem from Lee et al. 2012 states that any epsilon delta dp mechanism running on a uniformly sampled subset of data with a sampling rate nu guarantees this differential privacy. Okay, this is a, what is this thing? So I actually made a simple table to explain what this is. Let's say you subsample the whole thing. So meaning that you use the entire data set, and then let's say, and then run some algorithm, and this provides privacy loss 1, epsilon 1. But if you actually sample only 10% of it and run the same algorithm, then according to the theorem, the privacy loss will be only 0.159. It's a lot smaller than 1, right? If you reduce the sampling rate even more, like 1%, then the privacy loss is even lower. Why? It's because you have less idea about what the whole data set is if you have only few samples taken from the data set. Okay. And then we combine this privacy amplification effect as well as the moments accounted method we saw before. We apply this to variational inference, and this is one of the results we got. So if you just run the non-private latent Dirichlet allocation LDA method model for variation inference, then you get topics like this. Let's say I randomly select topic number 3 that has highly rated words like David, King, God, Son, Israel, and this is something biblical, right? And you see that probabilities assigned to these words. This looks very coherent and nice. And then this is our method. I was trying to find a topic that's similar to this biblical thing. So I also found David, Jonathan, King, Samuel, Israel, and so on. And you see, these words are very different from this. And the probability, assigned probability is also a lot lower. But somehow you can still see these are quite coherent as a topic. And the other method is as a comparison, existing method. We look at this. I was trying to find a similar topic, but I couldn't find it. And then I found one randomly selected topic here. I'm showing it. And then mount, display, animal, equipment. I don't know. There's not so much coherence here. And also you can see the assigned probabilities are very low, meaning that they have high uncertainty about this topic, these words for this topic. Okay. Right? So this was the example of topic modeling, how DP is applied to topic modeling. And then deep learning. So wake up. It's deep learning. So how many of you actually work on deep learning? Raise your hand. Don't be afraid. It's okay. Oh, okay, not many. Okay, deep learning.
So would you please go back previous slide, please? I am wondering that how do we know the coherent topics and how do you check?
So this is a very good question. And in our paper, we used perplexity as a measure. Yeah, but within the topic modeling field, there are still discrepancy between, people. What would be the good measure to use for coherence? But I mean, we basically, none of us are like topic modeling experts. So we basically use the existing measures like perplexity and so on. But I don't know, actually. I don't know what's the right thing to do. And a lot of debate is still there. Yeah.
I have some simple question. How long would it take to run the DP algorithm for large data set?
I don't think it's taking longer than user algorithm for large data set. In these examples, we basically add noise to sufficiency statistics or parameters, right? So that adding noise, drawing random noise from Gaussian distribution and then adding noise, this doesn't take so much time. I will go to that in this deep learning example. Yeah.
All right. And for the picture that you show, you have the L, the latent, and the M, right? What if the latent leaks out the privacy law? Is it important?
Oh yeah, it is. That's why we don't release it.
So
that's why I was saying.
It's very important, right?
Yes. For instance, these are telling us membership, right? So we don't release it. We have the exact same setting as before in the EM case.
All right, thank you.
Oh, was it this one? Take photo this one? Go for it. Okay. Yeah, we also do it sequentially.
For each data in the data set, or for how much? I'm not quite sure for this one.
In the setting of topic modeling,
In any sense, for let's say for if we have like large data set, so what is the number of J?
So in this example, we use the topic modeling, and we use the convention that LDA paper used. Basically, I think they were using. I don't know the number off the top of my head, but what I can say is this DP part doesn't require more. I mean, maybe it requires a little bit more because, as you said, maybe convergence is slower, but not drastically higher than the usual non-private variational inference, stochastic variational inference. And how many iterations do you need? I mean, it depends on the data, and depends on how noisy your data is, how good your initial parameters are, and so on. It depends on a lot of many things.
All right, thank you.
Okay. Deep learning. Okay. Wake up. Okay. Deep learning. Okay. So, how do we do deep learning these days? Stochastic gradient descent, SGD. We use SGD, right? So, how do we use this? In every training step, right, we subsample the data, some data, and we compute the loss, gradient of the loss with respect to the parameters, right? And in this case, I particularly wrote this as a data instant-wise gradient. So this is my G of t is the gradient at time t of xi evaluated at the data point xi. I mean, usually in deep learning, you don't necessarily look at this thing. You only look at this, right? The average over the mini batch. Over the data points in a mini batch. And then using this average gradient, you update your parameters. In the vanilla setting, you have learning rate, eta, that also changes over time, something like that. So you update your parameters. DPSGD, proposed by Abadi et al. This is extremely simple. So now what you need to do is you have one additional line here between these two. You basically clip the instant-wise gradient by C. So if the norm, L2 norm of the gradient per instance, data instance, is larger than C, you want to confine it to be smaller than C. Why? Because what matters is the sensitivity, right? And in the deep learning case, there's no way you can do sensitivity analysis because you don't know how one data point will change the gradient of this thing. So what they propose is, let's just forget about the really original way of doing sensitivity analysis. We just limit one data point's effect on the gradient by clipping like this. And then we add noise to the average so that this gradient, this sensitivity is reflected in this form. Okay, so this is DP, correct, technically correct DP algorithm. And then once you have this perturbed gradient, suppose we start with a data independent initialization, and then this is data dependent, but we noise up, right? And then the next parameter will be DP. As we saw before, it was, what was it? Data, it was a pre-processing invariance, right? The first property. And you do this over and over again. And then you can also compute the resulting privacy loss. And you get the finer differentially private parameters. Okay. Is it clear? Okay, so this is the three plots they showed in the paper. So they used a very small CNN, 2 convolutional layers, and 2 fully connected layers, and trained on CFR10 data. And they actually removed the privacy part on the convolutional layer. They assume that there is a public data you can freely use, and you estimate those convolutional filters using those private public data, so you don't need to worry about privacy there at all. But they only privatized the fully connected layer, the last 2 layers in the model. I think the problem is if you actually want to privatize all of them from scratch, probably the finer epsilon is very large, so they wanted to actually limit the epsilon to be somehow acceptable range, within acceptable range. So now let's look at the 3 plots. So they are showing the results for epsilon equals 2, 4, 8. As we talked about before, larger epsilon is less private, right? And you can also see that less private case, you get better accuracy. Yeah. And then this red trace is test accuracy. Blue trace is training accuracy. I don't know if you see. Okay. So there is no non-private case, so we cannot actually see the convergence, how fast it converges, and so on. But one thing I want to emphasize is that in this case we add the most noise, right, compared to epsilon 8. The more noise we add, actually there is a smaller gap between training and test accuracy, and people started looking into this more theoretically. This is basically, they're saying this noise addition due to DP constraint gives you better generalization. So this is something people start looking into it. Yes. No, it doesn't, because it's zero mean Gaussian. Yes. Yeah. Yeah. Okay. All right. Okay, so we talked about 3 different examples. Clustering density estimation with expectation maximization, and topic modeling with variational inference, and deep learning with stochastic gradient descent. Yeah, okay. Now let's, this is the last piece of the talk. It wouldn't even take 50 minutes, so. This is how people use DP in this industry setting. So Google claims that they use randomized aggregatable, privacy-preserving ordinal response. They basically collect your data. I mean, if you use, most of us probably use Google Chrome, right? And they, whether you know it or not, they use, they collect your data, you know, what kind of web pages you're going to, because they want a statistic. Probably they will sell it, I don't know. But anyways, what they're saying is, well, we collect your data, but we are not collecting the raw data. We will add some noise so that your individual privacy is protected. So how this is happening is in the following very simple mechanism. So we basically introduce, not we, but they introduce randomness in the data. So let's say they want to collect your data, but first they flip a coin. If the coin shows a tail, right, then they respond truthfully. So let's say, did this person go to google.com today? Let's say the truthful answer is yes. And the tail appears, right? And then we answer yes. And if the head appears, then flip another coin. So it adds more randomness. And then if it has, if it shows the head, and then you say yes, and then no otherwise. So what is the probability, after doing this, what is the probability that the answer yes will appear if yes was truthfully responded? Well, anyways, it's from here to here, right? This is 50%. And then here to here is 25%, another 25%. So it's going to be 75% of time, the true answer will be provided. So even if individual answers are all noise up, as a whole statistic, you can see what is the true answer, right? In this way. So this is another way of adding randomness in the response rather than adding noise directly. And another example is Apple Mac. Who has Apple Mac? Okay. Oh, a lot of us. So have you actually looked into security and privacy part? Go to security and privacy part. You will see personal data is either no logged at all, but is subject to privacy preserving techniques such as differential privacy. Yeah, they said differential privacy. You just learned about. Yeah. Okay. But I mean, there's a problem a little bit. They are saying on which applications they are using differential privacy techniques to collect your data, and also what mechanisms they use. They have this report that you can find it. But some issues I see as a person who work on DP is that we don't get to choose what epsilon we allow, you know. But they choose their own epsilon, and they changes every day for some reason. So this is a little bit questionable. Anyways, this DP is not some theoretical quantity anymore, and people started using it. So that's why I wanted to wrap up my talk with these examples. So as a summary of this whole lecture, I talked about privacy, which is a necessary concept to consider, not only to protect our own privacy against threats, but it also has a good philanthropical meaning, reasoning to it, if people use it correctly. And differential privacy seems to be a dominating notion due to its provable guarantee. And we saw only very, very small portion of the whole differential privacy field. It's a very new field, but it's growing rapidly, and a lot of people are working on it. So if you are interested, you can also apply to my group. Okay, thank you.
Is it possible to publish like a data set, the whole data set, in such a way that we can preserve the differential privacy instead of just statistics?
I mean, in theory you can, but usually the accuracy and privacy trade-off gets a lot worse if you want to publish the whole data set. So what people usually do is you either constrain the tasks you will do after you publish the data. So you only focus on certain statistic of the data and release them, how to noise them, and so on. Or like, for instance, you will only do linear query, for instance. Then the data you release, the issue is that you cannot have data release mechanism that can be accurate for any task, right? This is you cannot have that. So you usually have certain number of tasks you consider to do later on, and then you noise up, or you develop certain mechanism for that purpose only. It's like a no free lunch theorem. So you cannot get everything by adding some noise. Is masking something similar to anonymization? What people, so this is a little bit different story, but what people started looking into is actually cryptography mechanisms, combining cryptography with this kind of a mathematical notion of privacy together, because mathematical notion itself, there is a guarantee, but the thing is the privacy accuracy trade-off gets really bad usually, as you saw in the deep learning case. I mean, would you use classifier with 70% accuracy? Probably no. So people use cryptography methods to make a certain part private, and then only on top of that, use this differential privacy so that you add very minimal noise to have a similar guarantee. Yeah.
So you mentioned that differential privacy is the most popular notion. So are there any other notion of privacy as well?
Another thing is people talk about information theoretical notion a lot, and even like in that case they have units, right? Bits but in differential privacy, epsilon doesn't have any unit. So some people prefer the information theoretical notion. Yeah.
DP is about finding a better trade-off between privacy and accuracy, right? So a better algorithm is a one with better trade-off.
Yes, usually, yeah.
Can I have a question now? Yeah. So I was wondering how in practice how do you know what the value of epsilon is? I mean, how would say that a firm comes to me and the particular firm asks me the question, okay, this sort of data, and how would I give an advice that, okay, you should actually set the level of epsilon at this level, and how would you know the right number of queries that you would allow for a particular, the privacy budget? How would you set these two parameters in reality? How would you, is any way to approach this question?
Yeah, I mean, definitely this is still an open question, and a lot of people work on it. In some very simple models, I think the epsilon has interpretable meaning, but under most of the models, we don't really know what epsilon is, the quantity epsilon 2 means even. But what I can say is one could use different type of attack methods and see which epsilon is acceptable to be against these attacking methods. In case of Gaussian mechanism, for instance, we have this probability, right? So we only have the probability that how often this differential private guarantee will hold. And these values can be set by looking into different attacking methods and see whether your epsilon delta pairs will be actually against some number of attacking methods. Of course, then, I mean, if somebody else shows up with some different attack method, then maybe your selection, previously selected epsilon delta will not be robust. But yeah, this will be one way of choosing epsilon delta.
Okay, so I think let's take more questions offline. So for now, let's thank